All right, guys, welcome to your first video lesson. This is going to be where we go over our new topics, and then we're going to practice them in class. That way you get my FaceTime when you're doing your practice problems, so we can really go over questions and you're not stuck at home. So your lessons will be mostly videos that you watch before class. I'm starting here on our Canvas page. We're here in class, and I just clicked on the modules. This is what we went over on the first day. And I just want to show you that what you'll see, this is the box you've been working on for our first day. Here towards the bottom, right here, download the probability notes packet. That is where we're going to do our notes today. So you want to start clicking right there and getting the notes packet ready. Here is the notes packet that pops up. It's a PDF. Feel free to download it. Feel free to print it. But this is where you're going to be following along with the lesson today. We're going to start with probability. It is not a chapter in the book, so you're not following along in the book. These are our notes. We're going to do these first 3 pages today, and we're going to slowly go through it. So probability, what we're going to start with is basically different ways of counting individuals or groups and how many ways we can count things. So part 1 of today's we're going to look at notation, permutations, and combinations. So combinatorics right here, this is the branch of math where probability falls under. It is different possibilities and arrangements of objects. So that's what we're really going to be looking at. These aren't all that easy to decipher which one we're always going to use. So that's why when we do our work session, we're really going to talk it out and iron all this out. But we just want to get some problems under our belt to start. 2 types of events we're going to be looking at, independent and dependent. Independent events, we're talking about multiple things happening at once when we talk about these events. So selecting objects does not affect the choice and ways of selecting another object. A lot of this stuff we're going to talk about is with like basically dice, decks of cards, marbles. So for instance, I'll give you an easy one with independent events for a deck of cards. If you think about a deck of cards, 52 cards, if I was to pull one card out of the deck, like a magic trick, and I was to look at that card, and then I was to put it back in the deck, so now I have a full 52 cards again. Then I picked another one. The first card and the second card are independent of each other because I put the first card back. Dependent events, same deck of cards. If I was to pick a card out of that deck, but then not put it back, and there were only 51 cards left, then picking the second card is dependent because the first card is gone. It doesn't exist anymore. So that second card can't be the first card, so it is dependent on what the first card was. We're going to talk about independent and dependent events a lot more, just a basic introduction right there. But we always keep that in mind when we're thinking about many things happening at once. We're going to start with the basic counting principle of probability. Basically, this is saying you have multiple events that can be chosen in different ways, and you just want to know how many total ways all of those events can happen. So the formal definition talks about you have P events, you have P ways of choosing the first event, you have Q ways of choosing the second event, and what you do to find the total ways and outcomes is just keep multiplying your amount of outcomes together. Most of this probability stuff doesn't make sense until you start seeing examples. So we're going to start with our first 2 examples of the year right here. So example 1, okay, Rise, a freshman at West Virginia University, has to plan his fall schedule. So we've all just picked classes. We're here. So let's imagine if we had this for our college. So he has a choice of 4 math classes, 3 literature classes, 2 philosophy classes, 2 humanities classes. He can only select 1 course from each of these areas. How many fall course schedules are possible? So this falls under the basic counting principle because I'm only selecting 1 from each category. So I have 4 math classes, I'm only picking 1. I have 3 literature classes, just picking 1. 2 philosophy, just picking 1, and 2 humanities, just picking 1. So all of these events are independent of each other because the math do not matter with the lit, do not matter with the philosophy. So these are independent. So the basic counting principle says, hey, I need to pick a math class. How many math classes can I pick from? Well, I have 4 math classes to pick from. I have 3 lit classes. I have 2 philosophy and 2 humanities. And the counting principle says, hey, just multiply the outcomes possible. So 4 times 3 times 2 times 2. Feel free to use calculators all chapter and all year in this class. Never a no calculator situation. I have 48 outcomes or schedules possible. What that means is, for these possibilities, he can make 48 different schedules, because if he takes the same math, the same lit, the same philosophy, but then just changes humanities, it kind of changes the whole schedule. So 48 different schedules can be created. We're going to look at this now with a different sort of situation. Some of these will be dependent, some will be independent. So what we're looking at now is student ID numbers. Suppose that each student gets a 5-digit ID number. So I'm going to show you here on the bottom. So basically what we're saying is there's going to be 5 numbers that create a total ID. How many different numbers can be created? Well, if we think about this, you think, okay, how many digits are there? Well, when we think about that, we think about the numbers 0 through 9 for a total of 10 digits. So how many digits could be in the first spot of the number? I could have 10. It doesn't talk anything about repeat, so these are all independent of each other. So I could choose 10 or 10 or 10 or 10. But basic counting principle says pick one of the digits, multiply it all across the board, because for any one of these IDs, I could have the ID number 0, 0, 0, 0, 0. I could have 1, 2, 3, 4, 5. Any ID, there's 10 options for each of the spots. So if I put that up here, multiply that out, that is 100,000 possibilities. My second one, suppose no digit can be repeated. So I'm going to put out the same line of 5-digit number. Okay. Now, what I'm thinking about here, remember, this is just 10 possibilities. This is not the number 10. This is basically saying any number 0 through 9 could be in this slot of the number. So if you think about that, you start off an ID. It's saying I could still start with any one of the 10 digits. And we're going to multiply. But it now says can't repeat. So whatever digit this might have been, it was one of the 10 numbers. So I only have 9 numbers left because I can't repeat the first one. And now I can't repeat the first 2. And then I can't repeat the first 3 that happened. And then finally I only have 6 numbers left because 4 of them are already used. So this leads me to multiplying it out to just 30,240. Again, why are these two different? In the second one, I can't reuse a number. So I had 10 possibilities. Now I only have 9 left. All right, let's look at our last one. If no two adjacent means next to. Numbers next to each other can't be the same. So I'll change the color. So this is my blue one. So again, I have 5 different digits making up the ID number. Okay. And now, no adjacent, next to. Well, there's nothing next to the first number. So there's still 10 outcomes. So then next to this 10 possible, no, this is not the number 10. This is saying I have 10 different numbers I could put here. I can't repeat what I just had next to it. So there's only 9 left. So now let's create a number as we go. This is like a test number. Let's say the first digit was 3. After that, it just can't be the number 3. So I have 9 other options that could be this number. So let's say it's a 1. So now we get to the next number. How many possibilities are there? Well, this number coming up that we're creating just can't be the number 1 because 3 is not adjacent to this spot anymore. So I can use the 3 again, but I can't use the 1. So I can use every number except 1. How many numbers are there except the number 1? 9 numbers. So maybe this is a 3 again, or maybe it's a 4, or maybe it's anything but a 1. But I'm allowed to use 3 again, so let's just make it a 3. So now if you think, how many numbers can I put in this spot? It just can't be a 3. So how many numbers are not a 3? 9 numbers. And then the last number just can't be the number next to it. So 9 numbers. Adjacent just meant next to. So this is 65,610. And now this is just using the counting principle. And you can see there's not really a right way to do this all the time. You really have to think about whatever rules they put in place. But counting principle says multiply all of the outcomes. Okay, so that was our first page, counting principle. We're going to move on to our next page and talk about permutations, factorial, and combinations. So first, we need to understand what a factorial is. A factorial is counting without replacement. You multiply several values together, one less of the previous value. So what a factorial means, and look, it's this exclamation point in math. So if I had, for instance, 4 factorial, what that means to us is you do 4, then it says to multiply one number less each time until you're down to 1. So 1 less than 4 is 3. 1 less than 3 is 2. 1 less than 2 is 1. And then you stop. So 4 times 3 times 2 times 1, that is what 4 factorial is. One part here to notice is, what is 0 factorial? 0 factorial is 1, because what a factorial is basically making arrangements of things in a line. So I'll give you an idea. I want you to all imagine if I was going to line you up to walk you down the hallway, okay? And let's say our class had 6 kids in class. So I have 6 different students, 1, 2, 3, 4, 5, 6, and we'll make all different number. This is student 1, student 2, student 3, student 4, student 5, and student 6. What a factorial says is, how many ways can you put them in a line? Well, like they're in a line right now, but if, for instance, I could switch 6 and 1, I could put 2 here and 3 there. What a factorial says is, how many ways can I put them in a line? And the way it works is you basically say, okay, I have 6 slots, like we did on the previous page. I have 6 slots for kids to line up. How many ways can I do it? Well, for my first way, when I look here, I could pull any one of these kids. So I have 6 ways of doing it. But then one of the kids is gone. How many ways can I put the next person there? Oh, 5. And then one of the kids is gone. And then I have how many left? I have 4 left. Gone. Then I have 3 left. Gone. Then I have 2 left. Gone. And how many ways for the last kid? 1. And what do you do with counting principle? You multiply. So a factorial, 6 factorial, just is all about putting things in a row. That is why it leads right into a permutation, because a permutation is arrangements. This is about arrangements. When you think about arrangements, you should also think about specific order. You should also think about specific roles. Arrangements, orders, and roles is all when you think about permutations. Now, a factorial is a permutation, except you're just picking one at a time in a factorial. So groups of 1. That's why I picked 1 student at a time. So I had 6 students to choose from. I picked one of them. I had 5 students left. I picked one of them. A permutation expands this and makes it so you're able to pick more than one at a time and put them in arrangements, orders, roles. Again, a lot of this stuff starts to make a lot more sense when you do an example. So our example 3 here is for permutations. It's got a couple of things in mind. Okay. A high school honor society leadership team is comprised of 7 students. So I have 7 people in total. This is my total. I'm going to arrange the 7. Because my first question says, how many different ways can all of the members stand in a straight line for a picture? That's my first question. That's the one we're going to do here first. So if you have 7 people, you're putting them in a line for a picture. They're basically saying, how many ways can you grab a kid and put him in a place? Well, my first kid could be 7 kids to choose from. Then I used one of them, so 6 left. Then I used one more, 5 left, 4 left, 3 left, 2 left, 1 left. That is 7 factorial. Picking one at a time, putting them in a row or in a line or in an arrangement. There's a calculator video of how to do this. Okay, so if you have your calculator, that's great, pull it out. If you don't have your calculator, I will show you there are some apps. I will show you on the first day, I showed you, or I'll show you by the second day. There are apps that you can get for very cheap, even free, that you can mimic the TI-84 until you buy one. So 7 factorial. In your TI-84 calculator, you're going to want to turn it on. You're going to want to look for all of this probability stuff is under the math button. The math button is right underneath the alpha button. So I'm going to hit math. I'm going to go to PRB. I have a video on my website for you to follow this. There's a video there right now. So then I do math probability. I do 7. I find that exclamation point on the calculator, and that leaves me with 5,040. Your calculator does the math. You don't have to worry about that. So there's a follow-up question to this. We're not picking one at a time anymore. We're going to now put them in roles. So we're going to have a president. We're going to have a vice president. We're going to have a treasurer and a historian. So how many roles are there? There are 7 different roles. So permutations says to say NPR, meaning N is always total. N is always total. R is how big is the group size. For ordered or roles, we have 4 roles here. So it's saying from 7 people in the Honor Society. Make ordered roles, meaning give them assigned roles, which is a permutation, roles or arrangements. And make how big is the size? 4. What that means is way different. What we did here was picking one at a time. Now we're saying from 7 total people, how many ways can you assign 4 roles? Why does that matter? Because once someone gets president, they can't be the vice president. So you're picking 4 at once. 4 at one time. But what it also means is the president, vice president, treasurer, and historian can be the same 4 people, but they change roles. Permutations is the roles are important. So if 7P4. This is also going to be in your calculator. Watch the video. What you'll do is in your calculator do 7. Then you'll go to math again. Then you'll go to probability. And we will look for this NPR. NPR in our calculator. So I'll do 7. Then I'll go to math, probability, NPR. Put in the 4. And there are 7P4 in our calculator is 840. Okay, so permutations, I want you to think orders, roles, responsibility, and arrangements. Because now we're going to switch to combinations. Combinations is basically just picking groups from a total. How many groups can you pick? No order, no arrangements, no roles. It's just making groups, making groupings. You can see it's NCR. It's in the same place on the calculator where you see when you watch the video. And basically what it is saying, we start with an example. How many 5-card hands? So if you think about dealing out cards, when you pull your hand of 5, right? If I get 5 cards in a hand, it does not matter which card came first, second, third, fourth, or fifth. The order does not matter because I can easily take this card and I can move it over here and I can move this card over here. Meaning if this was a 7 and then this was a 7 on the cards, I can say, okay, I have a pair of 7s. It does not matter which card came first or last. So it's just a hand of 5. So I have 52 cards. That's sample size. That's all of them. I want to make groupings, meaning combinations, and how big are in each group. 5 people in each group. 52C5 in a calculator, 2598960. These are groupings because the order does not matter. We're not taking a picture. We're not giving them roles. We're not giving them responsibilities. Just groups of 5. Okay, this next example has a few mini examples in it. At Northeast Senior High School, there are 15 names on the ballot. So our N, our sample, is 15. Our total people is 15. 5 will be selected to form a committee. A committee is just a grouping, right? There's no committee leader. There's no committee second. It's just a group of 5. How many different committees can be formed? That's our first question. That's question number 1. So I have it now. It's just like the deck of cards. I have 15 people. I'm making committees of 5 people. 15C5 leaves me with 3,003. Again, the calculator video will show you that this is very quick math. Question number 2 in this changes it up, makes it more complicated. In how many ways can a committee of 5 be formed if each student has a different responsibility? So it is still the same 15. It is still the same committee of 5. But once you give responsibilities, once you give roles, once you give certain different characteristics, then the same group of 5 people can take on different roles. So it becomes a permutation. There are always more permutations than combinations. Believe it or not, this is 360,360. Why? Because this is just groups of 5. This is saying groups of 5, but count all the different arrangements of, your president, your treasurer, your historian, and then shuffle all those around. Our last one brings up a little bit more. This one brings the counting principle. It says if there are 8 girls, 7 boys, how many committees of exactly 2 boys and 3 girls can be formed? So no longer do we have 15 in total, because now we have subgroups. So we don't have that. We have 8 girls as the total number of girls, and we want to just get a group of 3 of them. A group of 3. So order doesn't matter. It's a combination. We have 7 boys. We want to get a group of 2 of them. Just a group. So it's a combination. But now our counting principle says, I need boys and girls. So I need to multiply, just like counting principle said, when I have math and humanities, I have girls and boys. So multiply that together. In the calculator, each of those goes, the 8C3 is 56 times the 7C2 is 21. You multiply those numbers and get 1176. We're almost there. We're going to do one more page, and it's just about some very specific permutations. These are permutations when things repeat, and then circular permutations, which is a very small subgroup of permutations. Permutations with repeat are very easy to see when you look at letters. So when you think about permutation, you think about ordering things. So given the following Scrabble tiles, if you've ever played Scrabble, you get your letters in front of you. Imagine if you had your letters and they were E-L-O-B-O. What this shows is all of the ways of arranging 6 different letters. Okay? We have E-O-O-B-L, E-O-B-O-L. We have a lot of ways there. They're putting them in arrangements because you make a word, the letter order matters. How many ways can the tiles be arranged if the O's are different? Well, this is pretty simple. We have how many total things? We have 5 total things. We want to put them in specific order. So you have 5, then 4, then 3, then 2, then 1 ways of putting them in order in a row. This is the same as 5 factorial, which is 120. The problem here is that we had 2 O's. So realistically, O's are just O's, they're just letters, they repeat. How many ways can the tiles be arranged if you are going to have a repeat? Well, that brings us to this permutation with repeat. The number of permutations of n objects, so in this case 5, of which p are alike. Well, this is basically saying we have two O's. So we have two O's that are alike, is n factorial, which we just did up here. That's 5 factorial. And then what you do is divide by all of the possible repeats. Well, O's repeat. I have two O's. So I have 2, and it says 2 factorial. It says right there in the formula. Factorial that. So you're basically dividing by all of the repeats. So they go away. So 5 factorial we said is 120. 2 factorial is just 2 times 1. That's over 2. So there's really 60 ways if the O's are exactly the same. There were no other repeats, so I didn't need the Q factorial or anything after that. Tennessee is way different. A lot of letters repeat. So it's saying, take letters of Tennessee. How many ways can you, if they were all unique, make a permutation? 1, 2, 3, 4, 5, 6, 7, 8, 9 letters. So if they were all unique, there'd be 9 factorial ways of arranging them. But I have repeated letters. It's not about how many letters repeat, it's how many of the same letter there are. I have 1, 2, 3, 4 E's. So 4 things repeat. Do I have any other repeats? Yup, I have 2 N's. So the formula says to multiply by how many other things repeat. So 2 factorial. I also have 2 S's. So I have to multiply by 2 factorial. You pop all that into your calculator using the factorial button, and you want to make sure that the denominator is in a parenthesis on your calculator so that it happens after the 9 factorial. This all gets done together. This would be 3780. Remember, if you want to try this in your calculator right now, please, please, please do so. But pause the video and see if you can get 9 factorial divided by all of that factorial. Why don't you try and set up the Alabama before I do it? Pause the video. See if you'd get it right. How many unique things are there? 7 letters in Alabama. What repeats? Just 4 A's. So I just have to divide by 4 factorial. This one was different because it had 4 E's, 2 N's, 2 S's. This one doesn't have that. So this one's just 210. These are permutations with repetition. Again, as you do a lot of problems, you'll see when do I use which one. The more problems we practice, the more comfortable you'll get with this. Our last topic of the day is what happens in a weird, random case if you are in a circular permutation. A circular permutation is basically, I want you to look right here, this is the most important thing. If you're in a magical room with no point of reference, see how this set of dials has a triangle to refer to, like basically saying this disk is on top. In these circles, nothing is on top. There's no A, B, C, D. There's nothing to refer to what is the point of reference in the circle. Imagine people sitting around a circular table, right? And there's 1, 2, 3, 4 people sitting around the table. If this room was basically, I don't know if you've ever saw Willy Wonka where they have that white room where everything just looks the same. If these 4 people got up and all shifted 1 seat around, then the same people are still sitting on their left and still sitting on their right. So nothing in the arrangement changed. If there was something like a point of reference, like who's sitting at the top of the table, then all of this would change. It's a very rare permutation, a circular, so don't get too confused here. Nothing changes if there are still basically, if n objects are arranged relative to a fixed point. That's this thing, basically saying if there's something in the room, like a door, if there's a person at the head of the table, then nothing changes. 4 things, 4 orders, 4 factorial. A circular permutation is saying if there is nothing point of reference, then the one group where they all switch but nobody actually is at the top or bottom of the table because it's a circle. This only happens if things are in a circle. This is saying to subtract 1 because this 1, these 4 arrangements, 1, 2, 3, 4 arrangements, are exactly the same. So you would just do 3 factorial. I would not worry too much about circular permutations. What it's saying is if there is very rarely a circular situation with no fixed point of reference, you just subtract 1 and do the permutation. Just take 1 away and do 3 factorial instead of 4. You'll see this a couple times in homework, and then you probably won't see it again. But I wanted you to know as we do our classwork, there is these circular permutations. Okay, this was all you needed to watch before class. Class time is going to be work time. You're going to be working on problems. You're going to be bring your calculator if you can. There's also apps for the TI-84. There's free ones. They're not all that great, but they can get you through the first start of school. A TI-84, if you have a TI-83, it's fine as well, as we talked about in class. Or you look for TI-84 apps. They're out there. That's it for your first video. We'll see you in class.